In this lesson, we're going to look at the exact trig ratios in special triangles. So there's a few angles that have very nice or neat trigonometric values. So if you take the sine of 49, for example, and put that into your calculator, you get a crazy number 0.75470958, and it continues and continues and continues. So 49 doesn't give us nice, neat sine values, cos values, or tan values, but there's certain angles that do. And because there's a few angles that we can come up with the exact sine, cos, and tan ratio, we use them a lot in problem solving in math, especially in calculus. So what we're going to do is we're going to derive these angles together using two different shapes to start with. So for one of the shapes, we're going to derive a triangle out of this guy, and then the other triangle we're going to derive out of a square. So it says that we're going to begin with an equilateral triangle with side length of 2. So I know that this guy is 2, this guy is 2, and this guy is 2. And in our other shape, we're starting with a square with side length 1. So I know this guy's 1, this guy's 1, this guy's 1, and this guy's 1. Taking a look at this first shape here, it now says split it in half to make two right angle triangles. So it's like if we were to take a line and bring it right down the middle, make a right angle triangle here. What would the dimensions be? Well, we can see this right angle triangle is represented right here. So let's fill in what we know. So what we know is this side length is 2. How about the bottom side length? Because this is an equilateral triangle, when we bring down a perpendicular line like this, it's going to split this exactly in half. So this is going to be 1. How about this side length over here? How could we find it? Well, we could just use the Pythagorean theorem. If we call this guy our C and this guy, let's do it in red. If we call this guy our C and this guy our A and this guy our B, we can just solve for A by doing A squared plus B squared. So we'll have A squared plus our B squared is 1 is equal to C squared. And let's just solve this. We have A squared is equal to 2 squared minus 1 squared. So 4 minus 1, which is 3. So A is just equal to the root of 3. We're not going to do the plus or minus root because we're talking about distance, so length of a line, so it cannot be negative. So we're just going to put root 3 over here. So in this triangle, we found all of the side lengths. Can we find the angles now? Because we're trying to find the angles in these special triangles and figuring out what these really nice sine, cos, and tan ratios are going to be. So what must these angles be given this these length of the line of the sides of the triangle? Well, take a look back up here. We were told that this is an equilateral triangle, which means that we've got 3 equal sides, therefore 3 equal angles. So what must each angle be? Well, we'd just take 180 and divide it by 3, and we would get 60 degrees. So this guy in here is 60 degrees, and so is this guy here. And up at the top, this whole thing is 60 degrees. So let's fill it in our triangle down here. We know that this angle is going to be 60, so let's add in 60 here. How about the angle up at the top? It definitely looks smaller than 60, but what is it exactly? Well, we have an angle here, and because it's an equilateral triangle, this perpendicular line is going to bisect this angle. It's going to cut it exactly in half, which means that this guy here is 30 degrees. So now we have this right angle triangle. We have each of the side lengths here, and they're nice, neat numbers. Just this root 3, if we actually put root 3 in the calculator, it's not a nice number, but just how it is right there, it's very easy to work with. And we have angles in the triangle. So now I can find the sine and cos and tan of each of these angles, and they're going to be really nice numbers. So let's try the sine of 30. So if we're talking about this angle right here, if we're looking for the sine of this guy, we're going to go opposite over hypotenuse. So the sine of 30 should be 1 over 2. And we know that that's true. We can prove it in our calculator. Just checking what's programmed into our calculator, sine of 30 will equal a half. Let's try the cos of 30 now. So cos is going to be adjacent, which is root 3 over 2. So the cos of 30 is always going to be root 3 over 2. Let's take a look at 60 now. We can find the sine of 60 degrees. We would take the opposite over the hypotenuse, so root 3 over 2. So that means that the sine of 60 is the same as the cos of 30. And let's take a look at the cos of 60. It's going to be adjacent, which is 1 over hypotenuse, 1 over 2. So these angles of 30 and 60 come up in problems a lot. The reason why they do is because look at their beautiful cosine and sine ratios. They're so neat and easy to work with. Let's take a look at another angle that has really nice sine, cosine, and tangent ratios. Let's go back to our square of side length 1. It says split the square into 2 triangles and solve it. So if I take a diagonal across just like this, we would be left with this triangle right over here. So here's our right angle. What are our side lengths? Well, this guy would be 1. This guy would also be 1. How can we figure out this guy here? Well, we can use the Pythagorean theorem again. So we've got C here. We can call this guy A. We can call this guy B. And let's fill it in. So we have A squared plus B squared equals C squared. So 1 squared plus 1 squared is equal to C squared. So it's going to be 2 is equal to C. So our C is going to be equal to the square root of 2. So we can just put the square root of 2. The square root of 2 isn't a nice number, but we can work with the root of 2 in equations. It's a nice, neat number. How about angles now? Can we figure out what angles are in this triangle? What the angle measures are? Well, we know that this used to be a right angle. And we have a square, and this diagonal, therefore, is going to bisect that 90-degree angle, which means it's going to cut it in half, which means what we're going to be left with is 45 degrees. And that goes the same for this corner here, because it's a nice isosceles triangle, so these two angles are going to be exactly the same. So we know that this angle measure is 45 degrees, and same with this angle measure. So now we have all the possible measures in this triangle, and now we can start to find the sine, we can start to find the sine and the cos of 45. So let's do it. We have this beautiful triangle, all the side lengths, we can find all the ratios. Let's find the sine of 45. So if we find the sine of 45, it's going to be our opposite over hypotenuse. So it's going to be 1 over root 2. And how about the cos of 45? The cos of 45 is going to be adjacent over hypotenuse, 1 over root 2. Interesting. So the sine of 45 and the cos of 45 are exactly the same. And the reason for that is the hypotenuse is always the same, but opposite and adjacent sides are exactly equal because we have a isosceles triangle. So because of that, sine and cos are the same. If we were to find tan, tan would just be opposite over adjacent. It would just be 1. Same with these guys here. We can figure out tan of 30 and 60 from those triangles. So let's summarize all of the ratios we just found. So the sine of 30, just go back to what do we find the sine of 30 to be? We found the sine of 30 to be a half. So we're just going to copy what we learned by deriving these special triangles. We're going to copy it into our little chart here to help us memorize. So the sine of 30 worked out to be 1/2. And the cos of 30 worked out to be root 3 over 2. The sine of 45 worked out to be 1 over root 2, and the cos was exactly the same because adjacent adjacent and opposite were the same. And then the sine of 60 was root 3 over 2, and the cos of 60 was 1/2. So really, we just need to memorize 3 values: half, root 3 over 2, and 1 over root 2. Once you got those 3 values, they just sort of repeat an interesting pattern. 30 and 60 are from the same triangle, so opposite of 30 is going to become the adjacent of 60 and so on, which is why these ratios are equal to each other. And then we know the sine and cos of 45. 45 degrees comes from a triangle that's isosceles, and opposite is going to be equal to adjacent, so these two are going to be the same. So let's figure out tan, and we can figure out tan by just taking a look at this guy here, just figuring it out right from the triangle. So if we do the tan of 30, the tan of 30 is going to be 1 over root 3, opposite over adjacent, and the tan of 60 is going to be root 3 over 1, opposite over adjacent. We can do the same thing for 45. tan of 45 is going to be opposite over adjacent, 1 divided by 1. So let's fill in for tan. We found out that the tan of 30 is 1 over root 3, and the tan of 45 was 1, and the tan of 60 was root 3 over 1, or just root 3. So there's another way to figure out what the tan of an angle is, and that's by using the identity that tan of an angle is equal to the sine of that angle over the cos of that angle. So we can prove that very quickly just using what we know about tan, sine, and cos. So if we were to take a look at what sine over cos would be, well, we know that sine is opposite over hypotenuse, and divided by cos, I'm just going to write it like this, divided by cos, cos is adjacent over hypotenuse. Well, how is this equal to tan? So we know that to divide a fraction, a fast way to do, just flip it and multiply. So this would be the same as opposite over hypotenuse times the reciprocal of adjacent hypotenuse, so hypotenuse over adjacent. And then our hypotenuses would cross out because hypotenuse divided by hypotenuse is just going to be 1. So this is going to work out to that tan is equal to just opposite over adjacent, which is exactly true. So what we did is we proved that sine divided by cos, sine of an angle, the sine ratio over the cos of that same angle will give you the tan of that angle, just going to equal opposite over adjacent. So knowing that, we could also find out all of these values by just dividing sine divided by cos. So if I wanted to know the tan of 30 degrees, I could just take the sine of 30 divided by the cos of 30. So if I were to just work it out on the side, I take the sine of 30, 1/2, divided by the cos of 30, root 3 over 2, flip it and multiply. Those 2's will cancel out, and look what we're left with, 1 over root 3. There it is. We can do this one quickly in our head. If we take the sine over the cos, 1 over root 2 divided by 1 over root 2. Doesn't matter what that thing is. If we're dividing something by itself, it's always going to be 1. Take a look at this guy here. If we take the sine divided by the cos, we would look at root 3 over 2 divided by 1/2. We know we're going to flip and multiply, so root 3 over 2 times 2 over 1. Those 2's will cancel out, and we just be left with root 3 over 1. So that's another way that we can find tan. So really, you only again need to memorize 3 values: our sine of 30, our cos of 30, and sine of 45. Everything else we can just figure out that sine and cos of 60 are just going to be the opposite of sine and cos of 30, and sine and cos of 45 are going to be exactly equal to each other. We don't even need to remember these values. We can just derive it using this property that we learned here, that the tan of an angle is just equal to the sine over cos. So now let's work on simplifying some trigonometric expressions. Let's use all these values that we've just derived and figure out if we can come up with actually an exact value for this. So we could just plug this all into our calculator and we're going to get a decimal, but our task is, can we find an exact solution? So we shouldn't have to use our calculator at all. So one property that we're going to need, we're going to learn more about it in grade 11, but it's written on your sheet. It's called the product rule of roots. So it looks like this. If you were to take the root of A times the root of B, we can rewrite that as the root of A times B. So here's an example. If we have the square root of 2, which we can't simplify anymore, square root of 2 is, it's not like it's a perfect square. So square root of 2 is just a decimal, so we would just leave it that way. Multiply with the square root of 3, also not a nice number. This would be equal to the square root of 2 times 3. As long as they're both under roots, and they're both the same type of root, so we haven't seen anything other than a square root, but actually there's all of our life, and we might have not known this, but there's been a little 2 there, and that's where the word square comes from. We're looking for the square root. But we could look for the third root and the fourth root, and that's going to come later. So as long as we're looking, the roots are the same, we can multiply what's inside, and this is going to be equal to root 6. So let's keep that in mind, that property in mind, when we're simplifying these. So taking a look over here, let's fill in, instead of putting sine 45 into our calculator, we know what the sine of 45 is. It's in our special triangle. It's just 1 over root 2. So let's replace sine of 45 with 1 over root 2. How about cos of 45? Do you think you have them memorized already? Well, came from that isosceles triangle, so the sine and cos are going to be the same. 1 over root 2. How about the sine of 30? What was that guy? That was a half. So I'm going to put a half. And now the sine of 60, that was root 3 over 2. So we do have an exact value, but we have to simplify it as much as possible. So we're going to do BEDMAS, we're going to do our multiplication first, and then we'll add if we need to. So if we were to multiply these two, what would this become? Well, we're going to multiply the top, so 1 times 1 would just make 1, over root 2 times root 2. Let's use this property here. Both of them are square roots, and they're multiplying, which means that I can just multiply the numbers inside the square root. So this would become square root of 2 times 2, which is 4. And then on this side, we have 1 times root 3, which is just going to be 1 times anything, it's just itself. And then at the bottom, we have 2 times 2, which is going to be 4. Is there anything else I can do here to simplify? Well, I know what square root of 4 is. It's just 2. So let's rewrite this as 1 over 2 plus root 3 over 4. Now, is there anything we can do to simplify? Well, yeah, we can make this one big fraction. So I'm going to multiply the denominators by 2 and the numerator by 2 of this fraction. So now we're going to have 2 over 4 plus root 3 over 4, and we can make this one big fraction, all over 4. And at the top, we're going to have 2 plus root 3. Should we put this in our calculator now to simplify? No, because we're going to get a decimal. Root 3 is not a nice number. So this is an exact simplified answer. So we are done. We can check if we've got time, if we've got the correct answer by using our calculator. We could put sine 45 times cos 45 plus sine 30 sine 60 press equals, and then take a look at what 2 plus root 3 is, all divided by 4, and the value should be the same. But here is the exact value. Let's try one more example together, and then you can work on the last one on your own. There's one little change that I do want to make though. Let's change this guy here from tan. Let's change this to cos. Okay, and let's start to solve it. So just like last time, any exact ratio we can fill in, we're going to fill in. So I'm going to start off with writing 1. So we've got 1 minus cos of 45 is just 1 over root 2. Use your table if you need to. Times the sine of 30 is 1 over 2. Minus 2 times the sine of 45. So that's another 1 over root 2. So this looks crazy complicated. So where would we even want to start? Well, let's start with BEDMAS, and let's do the brackets first. So what's inside these brackets? Let's bring these two like terms, or let's bring these two fractions into one fraction by subtracting them. So I'm going to put this guy over 1, so 1 over 1. What could the common denominator be? So this denominator is root 2, this denominator is 1. If I just multiply this denominator by root 2 and root 2, then they're gonna have the same denominator. In the numerator, I'm gonna have root 2. In the denominator, I'm gonna have root 2 minus 1 over root 2. So now the denominator is the same. I will be able to subtract them. So let's keep going. I'm eventually gonna have to multiply it by a half. I'll do that after. This guy here, can I multiply these right away? Let's put this over 1. We're gonna multiply the numerator. So 2 times 1 is 2. all over 1 times root 2 is root 2. And then we have, let's see what else we can simplify. We can simplify this guy because their denominators are the same now. So we can just do root 2 minus 1. That's going to be just root 2 minus 1 all over root 2. And then we're going to multiply that by a half, and then minus 2 root 2. So still following BEDMath, let's do multiplication next. We can multiply these guys. I'm going to multiply the top and multiply the bottom. So root 2 minus 1 times 1 is just going to be root 2 minus 1. And root 2 times 2 is just going to be root 2 times 2. But we usually write it with the whole number first. So instead of root 2, 2, we're going to write 2 root 2. So here's what I mean. The numerator, again, root 2 minus 1 times 1 is just going to be root 2 minus 1. All over root 2 times 2, just put the whole number in front and then the root second. And then we have minus 2 root 2. So in grade 10, this is as far as we really could go. But can we push ourselves a little bit more and combine these fractions? Well, they have to have the same denominator. Do they have the same denominator? They're close, but not exactly equal. What they have in common is root 2, but this one is missing a times 2. So let's do that. Why don't we just multiply it by 2 and see if the denominators are going to be the same. So we have root 2 minus 1 all over 2 root 2 minus 2 times 2 is 4 over root 2 times 2 is 2 root 2. So now the denominators are the same. So now the denominators are the same, we can rewrite this as root 2 minus 1 all minus 4 all over 2 root 2. And we can finally simplify this to root 2 minus 5 all over 2 root 2. We can check to make sure our answer is accurate. If we put all of this guy in the calculator and press equals, and then we put this guy in the calculator and press equals, it should give us the same numerical value. But no, because it asks us for an exact answer, you shouldn't need your calculator at all. And we didn't use our calculator all the way to the very end.